All right, section 9.8, power series. And to kind of give a little bit of a what's going on in this, let me remind you where we were last time. You guys told me from your homework that you thought it was a pretty straightforward assignment. I would say that that's probably apt description, right? Yeah. So what were we doing in that section? Well, we saw in 9.7 that functions like f of x equals e to the x can be approximated by polynomial functions. Now we will expand this idea to find exact representations as opposed to approximations by infinite series. These infinite series are called power series. Okay, so what we did in the last section was called Taylor polynomials, right? And we're doing power series today, and I can't remember if it's, let me check just to see which day it is. It's Friday that we'll actually talk about the Taylor-Maclaurin series that will continue kind of merging together what we're going to talk about today with what we talked about last Friday, okay? So today we're going to talk about power series. And to start with, let me give you a, wow, that was not really spelled right at all. A more concrete definition instead of a generalized touchy-feely one that I just did, because that's what I just did, right? It's not very mathematical. So power series. If x is a variable, then the summation from n equals 0 to infinity of a sub n x to the n, which would be a0 plus a1x plus a2x2, x squared rather, plus, we'll write it one more, a3x3, and so on. Continuing that process forever. It's called a power series. More generally, summation from n equals 0 to infinity of a sub n times x minus c to the n, which would be a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, and so on, is called a power series. Centered at C. make one claim where C is a constant. Okay, so how does this look, or how is this different than what we've been doing in sections 9.1 to 9.6? Well, there's an x in it, right? There's a variable. Prior to now, we've been dealing with summations of simply numerical series, right? It's a numerical series, numerical sequence. We've added all the terms together and so forth. And now there's a variable involved. That's the primary difference in what we're doing. So when we've talked about things converging and diverging, we haven't had this extra variable quantity to concern ourselves with, right? They were just numbers. Okay, a series of numbers that was infinite, but they were just numbers. And now we have a series of variable terms. So let me give you just a couple of real quick examples so you can see what these look like. And then we'll do some problems with them in a moment. But this is just what these look like. So for example, if you had the summation from n equals 0 to infinity of x to the n over n factorial. This would be an example of a power series. And if we wrote out a few terms, right, we plugged in 1, we plugged in 2, and so forth, it would look something like this. It would be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And this would be a power series centered at 0. If we looked at one that was centered somewhere else, let me give you one example of what one of those would look like. Still n equals 0 to infinity. And we'll go with an alternating one, a negative 1 to the n of x plus 1 to the n. So this would actually be 1, and then if I did it term by term, I'd have x plus 1, and then I'd have a positive, and then I'd have x plus 1 squared, and then I'd have a negative, and I'd have x plus 1 cubed, and so on. And this would be a power series. But where would it be centered? At C, but what is C?
1.
Close.
-1.
-1. Yeah, it'd be a power series centered at -1. Okay? So we're evaluating them just like we evaluate with numerical, just the n's involved. We just have x's in our problem when we're done. All right, so we don't come out with a concrete number, or we aren't able to say that this converges or diverges, because it's more complicated than that, because there's variable quantities that are going on. So how do we decide whether things converge or diverge if there's variables going on? Well, that's actually what we're headed to next. Theorem 920 says the following. For a power series, centered at C, precisely one of the following is true. So the first case is the simplest. It could be that the series converges only at C. So think what would happen. Let's just use the example number 2 that I wrote above. If you let x equal the C value, which would be -1, right? What would happen to all of the terms on the right?
Well, it would just be 1. Just be 1.
It would just be 1, because all the rest of them would be 0, right? So if I actually let x equal x equal -1, all of these would go away forever, right? Like they'd all go away. So it's definitely true that we at least get convergence at the C value we're talking about, wherever it's centered. Does that make sense? Okay, because we only get one term. Okay, so that's one possibility. So there's not a possibility that says, oh, it diverges. There's not going to be one of those. This is sort of the loosest possible argument that says it's trivial at that point, right? It's trivial. So this is the trivial case. The second case, whoops, is there exists an R. Are you guys good with some notation? Can I write some there exists on there? Okay, if you haven't seen that E there right now, you need to kind of look at me right now and be like, something so I don't write more. Okay, so there exists an R. And R is a real number, exactly. That's the next thing I want to say. R is real, and R is positive. Okay, so we've got a positive real number such that the series converges absolutely for x minus c less than r, and diverges if x minus c, these are absolute values of course, is greater than r. And you might be looking at that and saying, well, you left something out. What did I leave out in that case? The equals to r. So what happens when it equals to r? And the answer is not quite so clear. It's kind of like when we did the ratio and root test. What happens when it actually equals 1? Well, it doesn't work, right? We've got to try something different. Well, if it actually equals r, we actually have to figure out what happens at those points independently. All right, there's a different step, an additional step, and we'll see an example of that, okay? So, but we do know for sure that it splits it into two cases, and it just leaves this gray endpoint areas that we have to be concerned about. The third possibility is that the series converges absolutely for every value of x. So every value of x is going to work. Okay, so that's a possibility as well. A couple other definitional things to be aware of about this sort of idea of things converging or not converging. That R, so when I said R, and even before I said R is a real number, you assumed that it was, Ethan, because we like to use letters that sound like the descriptive words we're using. The R actually isn't used as R because it's a real number. It's used because it's actually representing the word for radius. So let me give you a definition that talks about that.
Can you give me the third one?
Sorry.
Series converges absolutely.
For all x. That upside down A means for all. You got it. Okay.
Is this for proving conversion? No, wait. The second one.
Yeah, it will converge absolutely for every value. So actually, give me just a second with our definitions and we'll come back if there's still a question. So R is called the radius of convergence. Of the power series. In case 1, we say R equals 0. Because it only converges at that single point, right? Case 1 over here is it actually converges only at C. There's no radius. There's no interval of numbers for which it converges. So we say that the radius is equal to 0. In case 3, we say that r equals infinity. Okay, we get all of the radius, all possible values, lengths of values, and so forth. The set of values for which the power series converges is called the interval of convergence. So you could be asked to find the radius of convergence, you could ask to find the interval of convergence, but they're really similar processes. So we're going to use the same examples and find both items. But when you get to your homework, please be careful what they're asking for. Your homework actually splits them up in such a way that some questions just say find the radius, and some just say find the interval. Okay? So you're not necessarily going to do both of these things on all your problems. It just depends on what the question's asking for. Okay, I'm not going to have enough space to finish on this slide, so I'm going to switch slides. Is everybody good with me switching the screen? Yeah, okay. All right, so here's our example, and I'll do it as though it's like a part 1, part 2. So we're going to find the radius. This will be part 1. Of convergence. And then the second thing is we're going to find the interval of convergence. And our first example that we're going to do is the summation from n equals 0 to infinity of n over 2 to the n times x to the n. All right, so what you're going to see us using a lot with the power series is you're going to see us using the ratio test a lot. And that should come as no surprise because you're going to have x to the n's everywhere, okay? I mean, x to the n's or x minus c's to the n's. I mean, that's going to be kind of one of those triggers that we saw before with ratio tests. So you're going to see ratio test used all over the place. So to start with, we're going to use the using the ratio test. We're going to take the limit as n goes to infinity of a sub n plus 1 over a sub n, which for us is the limit as n goes to infinity of n plus 1 times x. We could. That would be another possibility. Over 2 to the n plus 1. The problem on this one with using the root test, Ethan, is that we have this random n going on here. Where is my problem? That would cause us some problems with the root test. If we didn't have that part of it, the root test would look very nice. But having that part of it's not going to look so nice. Right? Because we have the nth root of n, not a good place to be. So, okay, and then instead of dividing, I'm actually going to write the multiplication of 2 to the n over n times x to the n. Okay, is everybody good with that step? Man, there's a lot going on. We should simplify that because it's a mess. All right, so somebody tell me what's this going to simplify to? Let's start with the x to the n plus 1 part. Right, these two can simplify so that I will end up with just an x on top, like Hannah said. That's right. So we have just an x on top. How about the 2 to the n parts? Yeah, I'm just going to have a 2 on bottom. And what else do I have? Oh, the other parts that don't simplify, right? All right, don't go canceling those ends out. Y'all know better than that. All right, the good news is that at this point, you do know how to simplify the n parts of this. We've been doing lots of limits long enough to know that this would be multiplication by 1 over n, right? So my limit as n goes to infinity would be, I've got this x over 2 part, which could still be positive or negative depending on what the x values are, agreed? So the absolute values are super necessary there. The other part doesn't matter whether I have the absolute values, but I end up with 1 plus 1 over n over 1. And of course this goes to 0, so this whole piece goes to 1, right? Yeah. So really I end up with just x over 2 absolute values. That's what my limit is. So ratio test. The ratio test tells us when something converges. Based on what? When do we know what, if I were given a number, if this ended up being a number, not an x, something at the end, how would I know whether this converged by the ratio test? If it's less than 1. So if this is less than 1, it will converge, correct? Yeah. So less than 1, it will converge. So I need to figure out what x values that means that x could actually be to make that happen. Well, it's a simple inequality, right? So absolute value is the same thing as having a negative 1, like this. Less than x over 2 is less than 1. You good with that? So what would that mean I need to do? Multiply by 2, right, absolutely. So this means that I have negative 2 is less than x is less than 2. Everybody good with that? So if my x values are between negative 2 and 2, it will converge absolutely. So knowing that right now, I can almost answer both questions I was asked. The first question I can definitely answer. What is the radius of convergence? It's 2, right? It's the distance on either side of 0, because this is centered at 0, right? It's a distance on either side of 0 that I can go away from 0, and that would be 2. So my radius of convergence is 2. So that's sort of answering part A or part 1 or whatever I called it up there. I think I called it 1. Okay? So part 1, radius of convergence 2. Now the interval of convergence is sort of almost there. We know it goes from negative 2 to 2, and we know that outside of that, right, if you're bigger than 2 or smaller than negative 2, it's going to diverge, right? That's what the ratio test tells us. But it is inconclusive when it equals that 1, which would be our 2 when we multiplied by 2, right? So what happens on the endpoints? That's where we are. What happens when x is equal to 2? What happens when x is equal to negative 2? Well, we plug the negative 2 and the positive 2 in, and we see what happens. Okay? So that's where we are. We are at the point where I need to figure out what happens when I have negative 2 and positive 2. So for x equal negative 2, we'll start with that one. Actually, let me make one more statement over here before I do that. So I said this out loud, I just didn't write it down. So this converges absolutely for negative 2 to 2, right? We just don't know what happens on the endpoints yet, whether it really converges still or whether it diverges. Again, that was more of what I just spoke, but I didn't write it down. Sorry about that. All right, so diverges outside the intervals. But what happens at those endpoints themselves? So at -2, what happens? So if x is equal to -2, then my summation from n equals 0 to infinity looks like n over 2 to the n times -2 to the n. That's what it is. So simplify for me. What does this simplify to? So all I did, guys, is I took this sequence and I plugged in -2 for x. Okay? Are we good with where it came from first? Yeah? Okay. So how am I going to simplify, in particular, this part right here, right? What's going to happen here? It is going to become -1 to the n. So there's an n still here, right? And there's going to be a -1 to the n here as well. So you can think about this piece right here as being able to be separated as -1 to the n and 2 to the n. And the 2 to the n will cancel with the 2 to the n we have in the denominator. So what kind of a sequence is this? It is alternating. And from the alternating sequence, alternating series, excuse me, we know that this will converge when? How will we know that this converges? That's ratio test. Good try. If it were geometric, but it's not geometric because I've got the n in front.
Versus infinity 0.
Okay, so limit, right?
Yeah.
So the alternating series test,
Diverges versus infinity.
the limit without the negative part. If the limit without the negative part of this is n, okay? So you, if you want, you can go like this. I don't care, but this would be the limit of n. Okay, so the limit without the alternating part. If it goes to 0, it's going to converge. And if it goes to infinity or to another number, it's going to diverge. What happens here? It's infinity, right? This is infinity. So this actually would diverge. So it diverges at x equal -2. So let's try it at x equal to 2 now, okay? So that's the second piece, x equals 2. So I have the summation from n equals 0 to infinity of n over 2 to the n times 2 to the n. What do I get? Yeah, summation of n. Is that going to converge or diverge? Diverge, why? Or by what test? Yes, diverges by the nth term test. Remember, we can't use the nth term test on the other part because it was alternating. The nth term test is only for a positive series, positive sequence of values, right? So, the nth term for divergence test. So, our interval of convergence is actually what?
Still -2.
Yeah, with open intervals, right? Our interval of convergence actually really does only include from -2 to 2, and it's an open interval. If this sequence, let's just say for fun for the moment, just change it up at this very moment right here. If this instead had said, right, change my highlighter, here, and it had ended up being 1 over n at this point, okay? Then the 1 over n series diverges because it's harmonic. But if it were the alternating part back from part A, and it were alternating, right, times 1 over n, that would converge. So you can end up with open interval on one side and a closed interval on the other side. All right, that's a possibility, or they could be both closed. So all three possibilities are there, okay? So completely open is what we just got, completely closed, or half open, half closed intervals are possible. So you really do have to check both endpoints. Okay, let's try another one. Well, any questions on this one before I go on? I'm sorry. Okay, Let's try one more then. This one's briefer. How's that? That one was kind of the meatiest one I had for us today. Same directions. Find the radius of convergence, find the interval of convergence. Again, you'll only be doing one or the other on your test or on your homework, blah. We're going to do k equals 0 to infinity of k factorial x plus 1 to the k. So again, factorials, red flag for ratios, right? Ratio test. So using the ratio test, we have the summation from, limit, that's right, limit into infinity of a sub n plus 1 over a sub n. And for this sequence, that would, or this series, excuse me, that would give us k plus 1 factorial on top. And we would have x plus 1 to the k plus 1 on top over k factorial on bottom and x to the k, x plus 1 to the k on bottom. Okay, so again, absolute value signs are absolutely critical for what we're doing now because we're dealing with variables. We had lots of cases when we were dealing with all this stuff earlier where absolute values were just irrelevant. I mean, really, because they were all numbers that were already positive. But variables don't have that feature. What do you notice canceling out? Okay, so I'm left with a k plus 1 on top. Is that right? Yep. Okay, so this piece cancels with the k factorial part of this piece, leaving me with just k plus 1. What else cancels or simplifies or whatever? Yep. X plus 1 to the k.
Should you be saying that k is going to infinity?
Yes. I have it since we've been using n's more frequently. Thank you, Hannah. Yep. Okay. A sub k, a sub k. Nope, you're right. Should not be to the k. We'll get it all worked out. You guys are keeping me on my on the straight and narrow, right? You are. You're doing a good job. All right. Do I have it all up there now, right? Is it okay? All right. Okay. Let me ask you a question. Where is this power series centered? It is centered at -1, kind of like that second example I gave at the very beginning, right? Centered at -1. Okay, so this is a ratio, and we know that it's supposed to be less than 1 for it to converge. So, what's the problem? Well, is it never less than 1, though? I mean, this is our question, right? Can it be less than 1? I mean, it can at one specific value.
If x is like 1 over
Close.
0.
If there's a 0 somewhere.
Oh, if x is -1.
Yeah, okay. So there's two possibilities. One possibility is that x is equal to -1. Oops. If x is equal to -1, then this piece of this becomes 0, right?
Isn't that C?
Isn't what?
C is
The second row.
Yes. It is. It's the first case. Let's see if I can get back to it.
C.
Yep. This one right here. See, there's always going to be the ability to converge because it always can converge at the intervals where it's centered, okay, wherever the centering is. So this will always converge at least in one location. In this case, that's what's happening, right? We've actually got this to converge here. But if x is anything else, then what happens to that k plus 1 term?
Diverges.
It's going to force it to go to infinity, the whole thing, and it's going to diverge, right? If x is negative, if x is positive, if x is any other value, then this piece right here is going to dominate all of what's going on because it's going to be infinity. And infinity times any other constant is infinity. So if x is anything else, oops, that's a e, oops. then this will diverge. And you guys already pinpointed it, and I'll write it down here too. It's case 1. We're in case 1 here. So what does that mean? Well, it means that the series converges absolutely, but only at x equal 1. Negative 1, sorry. X equal negative 1. So let's answer the questions. What is the radius of convergence? Yeah, it's 0. And this would be one where they wouldn't probably ask you for an interval of convergence because there's not an interval, right? The interval does not exist because it's only a specific point at which it exists. Make sense? So there's no diverging. That's not going to happen. It's always going to converge, even if it's super limited convergence, which would be this case. All right, homework for today.
Interval does not exist.
Yep. Page 654. Numbers 6 and 9. Those are the radius of convergence ones, and all the rest, I think, are interval of convergence, if I remember right. 15, 18, 1, 24, 27, and 33. Nope, that's 30 at the end. Can't read my own writing. There we go.